Our built environment are not contained within an internal space, but instead, our buildings are external, in which they are constantly exposed to wind, rain, snow, and very significantly, the sun. Throughout centuries, these villages have become massive cities in which their buildings consume massive amounts of non-renewable energies. This is one of the main causes for climate change, which has devastating effects such as earthquakes, flooding, forest fires, tsunamis, and many more. Our aim is to reduce carbon emissions by 70% in 2030 and then a further 90% in 2050, in which we hope to prevent the 2-degree temperature threshold rise. Solar shading is one of the many ways in which buildings can reduce their energy demands and meet user comfort expectations and needs, especially in modern buildings with large areas of glazing. Firstly, it reduces solar radiation penetration, which reduces overheating and therefore reduces the need for mechanical cooling. Secondly, solar shading devices should increase and distribute daylight, which reduces glare and also reduces the need for electrical lighting. Solar shading should also encourage solar gain in winter, which reduces the needs for mechanical heating. Note that total solar load is either direct radiation, diffuse radiation, or reflected radiation. Direct radiation carries 5 to 10 times more energy than diffuse radiation, whereas reflected radiation in built-up areas can also contribute to urban heat island effect. Successful solar shading design reduces temperatures by about 2.5 to 4.5 degrees on average on a south-facing facade. Earliest forms of solar shading design can be seen as far back as Vitruvius' 10 books on architecture. Overheating is caused by short-wave solar radiation, incident sunlight, cutting through the building envelope, mainly through the windows. This gets absorbed by the interior surfaces and objects, and gets radiated out as longer solar radiation wavelengths, which is then trapped inside the interior of the room. This is the number one cause for overheating, as well as electrical appliances and electrical lighting. Solar shading devices mainly occur around in or around the window details, which therefore has an impact on the views out, amount of diffused daylight, aesthetics, and most importantly, ventilation. We must find the correct balance between the effect of solar shading and these other parameters. The main principle in selecting the correct solar shading device is orientation. Orientation lets you choose the device and what type it is in terms of which wall it will be applied on. In the summer and at lower latitude countries, the sun has a high solar angle, whereas in the winter and early morning and evenings, the sun is at a lower solar angle. Understanding the position of the sun in relation with building orientation, seasons and time of day is crucial for optimizing the performance of solar shading devices. Firstly, shading can be achieved without physically designing or retrofitting devices onto the building envelope. Good landscaping can solve problems. Planting of deciduous trees, vines and shrubs provide natural shading where these prevent solar penetration of high-angle sun, whereas in the winter, the low-angle sun can penetrate through the bare branches. Research shows that the larger the leaves created more solar shading effect, and the higher the tree created more coverage. Further research shows that trees can reduce wall temperature up to 18 degrees with averages about 8 to 10 degrees on a summer south-facing facade. This reduces cooling load by 20% and reduces indoor temperature by 5 degrees Celsius. Advantages are that there are no further alterations needed to the building fabric if trees created a desired level of shading. Also, it is a passive temperature control feature which reduces urban heat island effect. Moreover, it improves air quality via evapotranspiration and also increases biodiversity. However, vegetation is only effective to shade low-rise buildings and dwellings due to their limited coverage. Also, make sure that there is adequate spacing between trees if natural ventilation is desired. BRE suggests that wide obstructions are not less than 30 degrees either direction of south-facing wall to maximize solar gain in winter as well as providing good levels of daylight. Note that the sun provides 14% of space heating demands in UK from direct and diffuse solar radiation. The amount of daylight depends on the amount of visible sky seen through the window, and to a lesser extent, the reflectancy of interior surfaces. This is very important in solar design as solar shading devices will affect daylighting and views one way or another. In addition, shading can be achieved through the natural shape and form of building elements. Taken as far back as the traditional Japanese minkas with overhanging eaves to block incident sunlight, to more contemporary buildings with the use of balconies, horizontal overhangs, and window recesses that provide a functional use as well as blocking out sunlight. A particularly effective design in reducing overheating and increasing daylight is the sawtooth roof typology. This type of roof is seen commonly in warehouses and factories, which is a functional design to provide daylight, ventilation, and solar shading. The picture of the roof faces south, with vertical openings to utilize north light, especially useful in art studios. The south-facing pitch prevents overheating and unwanted glare. Note that this is also an ideal place to place PV panels. Vertical sawtooth protrusions can also be very useful on east and west facades to catch and maximize solar gain in winter months. On the market today, there are many varieties of external shading, such as overhangs and canopies, fixed external louvers, horizontal light shells, vertical fins, egg-crate baffles, and so on. Overhangs and canopies are a common solar shading device that performs best at blocking high-angle sun from the south. Horizontal projection length is dependent on the height of opening and also the location of the building. Rule of thumb is that projection length is a quarter of the height of opening at low latitudes and up to a half the height of opening at higher latitudes. This is because low-angle sun exists at higher latitudes and therefore a longer projection is required and vice versa. If overhangs needed to be oversized, i.e. for a canopy or sheltered walkway, it is best to have the underside as a reflective material so that sunlight can still be reflected back into the interiors. In very hot climates or in countries close to the equator, it is best to shade the entire solar facade. Similar to overhangs, light shelves are horizontal projections that can be internal or external, which divide the glazing into two parts. Light shelves works best on south-facing windows. Principles of light shelves is to reflect incident light up into the ceiling and reflect back into the back end of the room, which reduces glare and distributes out daylight. Some light shelves are also tilted towards the interior to max out the lighting being reflected through. It is preferable to install light shelves on high ceilings with high openings so that it won't obstruct views out. For both interior and exterior units, it is best to have a surface with high reflectancy to reflect as much solar radiation and daylight as possible. Darker colors or surfaces may reduce reflection by about 10%. For the same reason as horizontal overhangs, it is not suitable for east and west facades due to the low-angle sun. External louvers come in many different types, ranging from horizontal, diagonal, vertical, fixed and movable, etc. This means that they can be fitted onto both south-facing windows and east and west-facing windows. It is best to use horizontal louvers for south-facing windows and diagonal or vertical louvers for east or west-facing facades to reflect summer sun and also allow winter reflection. Opaque louvers are most common, although heavy diffused glass louvers are also available. They are easier to control glare, therefore increase uniform daylight, but decreases shading effect. Louvers also come fixed and or movable. Movable louvers allows more flexible control in solar penetration, but is very costly and moving parts have more risk of failing. Fixed shading allows less user control but has no moving parts. It is logical to accept that fixed louvers blocks high-angle sun in summer or midday and penetrates in low-angle sun in winter, evenings and early mornings, which may or may not be a good thing. Vertical fins are best used on west and east facing facades where it is exposed to low angle sun, in which horizontal overhangs are made redundant. They reduce glare and solar gain as well as providing ventilation up the walls. Research shows that vertical fins at fixed angles can reduce solar radiation by 40% in a summer day. When possible, it is preferable to extend the vertical fin above the height of the window to allow for shading of higher angled sun. Tinted glazing can also be another solar shading and daylighting device. There are two types of tinted glazing. One is absorbing glass, which is body tinted, which ends up absorbing the heat from the sun. Second is reflective glass, which has a reflective surface. This may dazzle road users, pedestrians, and contribute to urban heat island effect. However, reflective glazing has better solar shading properties in preventing overheating than absorbing glass. Both types of tinted glazing can be used in facades that receive high solar gain. Depending on the amount of tint, it may affect the views out and daylight. It might be useful in interiors where daylighting is not so important. Window films are a low-cost retrofit option which can be applied on the interior and exterior of glazing, although exterior films tend to be better at preventing overheating but is less durable. However, both types of films can also act as a shatterproofing feature as well as reducing glare and reflecting in sunlight. Similar to tinted glazing, certain films will have effects on views out. Stronger tints can be applied onto rooms where privacy is a big issue. With both tinted windows and window films, once applied, there is no user control. There are also films which protect the interior from UV rays to maintain valuable pieces of artwork, clothing, historical artifacts, etc., which are very important in museums, art galleries, and retail units. Prismatic glazing contains triangular prisms that reflect and refract incident solar rays which diffuse direct light and or direct it into the ceiling. However, prismatic glazing seriously reduces views out. It is desirable to be used on roof lights and also in windows where views are not so important. Mid-plane glazing are small units sealed between panes of glass. This creates a stripe pattern view on the glass which can affect views in and out, but also increases privacy. In a fixed position, summer high-angled sun is reflected, whereas lower-angle winter sun is emitted and redirected. However, movable louvers inside the glazing are also available to increase flexibility, in which controls are powered by magnetic linkages. In double-skin buildings, these are installed in an independently ventilated cavity. Similar to tinted windows and window films, mid-pane devices are very easily cleaned and maintained, just like an ordinary window. Curtains are commonly used in domestic settings which provide the users with easily accessible control over daylight and glare protection. Curtains do not contribute significantly to overheating prevention since it absorbs and radiates solar heat as long wavelengths which gets trapped inside the room. Although the thicker the material, the better the insulating properties as well as providing privacy. Venetian blinds offer great user adjustability and glare control. These can be automated in areas where users cannot reach or have limited mobility. Translucent blinds are also available which transmit extra light and view but can be hard to clean. Because Venetian blinds have the same concept as light shells, it is best to consider light shells for larger openings instead of blinds, since it does not obstruct the view as much as Venetian blinds, since these blinds create a rather disturbing striped pattern. There are many other internal shading systems such as roller blinds, reflective roller blinds, Austrian festoon blinds, pleated blinds or fabric or paper blinds, Roman blinds, vertical louver blinds, most suitable for east and west facades, fixed solar screens, etc. These can all be manually adjusted or motorized. They all control daylight and glare to certain extents, but are not as effective as external devices to prevent overheating. Note that fabric with high transmittance may become very bright and when the sun is on it. This causes unwanted glare and problems for the unfortunate people operating computer screens inside the room. In such situations, CIBSE recommend a transmittance of less than 0.1 for shading fabric, and the room must have luminance of a minimum of 500 lux. Reflectancy is another important criteria. Light colour blinds avoid harsh contrast at nighttime between surrounding walls. Highly coloured blinds with non-zero transmittance may diffuse a wash of colour which can be distracting. For solar control, the side of the blind facing the window should be a light colour and preferably silvered to reflect out incoming sun. Dynamic skylight shading and photovoltaic sun tracking louvers are new technologies that are run by solar powered motors. They are dependent on the sun's position, in which louvers adjust automatically to reduce solar heat gain, glare and maximize daylight, but also control solar gain in winter. Flexible shading gives optimum comfort at different times of day and dependent on seasonal changes. This can be either vertical louvers or horizontal louvers or vertical fins depending on window orientation. Smart glazing controls glazing properties at different times of year. There are three main types of smart glazing. Firstly are electrochromic and liquid crystal glazing. This is where it becomes darker when an electric current is applied. Secondly is photochromic glass, which darkens in proportion to the degree of exposed sunlight. Thirdly is thermochromic glazing, which turns murky when it warms up, therefore preventing any solar penetration which causes further overheating. All in all, electrochromic glazing provides most user control and can be turned on and off. Mesh shading systems also shade the building from the sun and reduce solar heat gains, but also act as a desired daylighting feature which allow the desired amount of daylight through, as well as allowing various degrees of visual penetration. Research shows that increasing the number of panes in the window fixture decreases energy load in cooling, and therefore decreasing the window wall ratio will also decrease energy demands. However, views out will be compromised. Various calculations can give you a brief outline of determining window wall ratios. Ceilings should be of light material to maximize daylight reflectancy. With many types of glazing, internal and external shading devices, there are many combinations you can tweak, from fixed PV panels, fixed glazing and mid-pane blinds, case window with internal blinds, nighttime ventilator with a hopper window and sliding screens for privacy and security. Obviously, possibilities and permutations are numerous, and there are many more to choose from. Note that external shading devices can become very expensive and costly to maintain. Especially, it may disrupt with the ordinary window cleaning services of the building. Internal shading devices are usually cheaper and easier to maintain. However, they are not as useful as preventing overheating as external shading devices. Here are the most effective shading devices for certain orientations. Best to use horizontal solar shading for south-facing windows, which can reduce solar gain by 75%. Make sure shading device allows gap between fabric and device for ventilation. Vertical shading is best on east and west facing windows. More flexibility can be achieved through adjustable louvers. This provides 90 to 95% solar gain reduction. Horizontal or vertical fins can be used on southwest or southeast facing windows. It provides 60 to 75% solar gain reduction. The lower three devices are suitable for all orientations since movable parts allow optimum user adjustability. However, in comparison, they reduce daylighting and winter solar gain. In conclusion, solar shading can add architectural expression, texture and modulation of the facade, but it should respond to orientation, surrounding settings, use and function, and of course occupancy. These are all the parameters to finding the optimum balance between solar shading devices and the effect it has on views, daylighting, glare, ventilation, and user comfort. This video presentation only provides you with a rule of thumb in solar shading design. You must understand that solar shading is conjunctional with daylighting, ventilation, thermal comfort, and building fabric, where all are dependent on each other in designing how well the building performs as a single entity. For specific projects or briefs, it is best to carry out tests and simulations, such as a simple model in Heliodon, to more complicated calculations and simulations such as Ecotect. This is where tests and tweaks can be carried out to your building, where it will enhance its efficiency and energy consumption as best as possible to face the future changing climate.